Since the dawn of human consciousness, we've been obsessed with finding the center of things, the center of our villages, the center of our kingdoms, the center of our world. It's a deeply ingrained human instinct, this need to locate ourselves in relation to a focal point, to understand where the middle is, so we can make sense of our place relative to it. For thousands of years, across countless civilizations and cultures, we believed Earth sat at the very heart of creation, with the heavens wheeling around us in perfect celestial circles. The ancient Greeks developed elaborate mathematical models of nested crystalline spheres carrying the planets and stars around our world. The medieval Catholic Church incorporated this geocentric view into its theology, making Earth the stage upon which the divine drama of salvation played out. Then came Copernicus in the 16th century, who dared to suggest that perhaps we weren't quite so special after all. The sun, he said, held the central throne, and we were merely one planet among others, dancing in its gravitational embrace. This was revolutionary, even heretical. It challenged not just our scientific understanding, but our sense of cosmic importance. If Earth wasn't the center, what did that say about humanity's place in creation? The Catholic Church famously resisted this idea for centuries. Giordano Bruno was burned at the stake, in part, for suggesting not only that Earth orbited the sun, but that there might be infinite worlds throughout the cosmos. Galileo was forced to recant his support for heliocentrism and spent his final years under house arrest. But the evidence kept accumulating. As telescopes improved, as observations became more precise, the heliocentric model proved its worth. It explained planetary motions more simply and accurately than the geocentric model ever could. By the 18th and 19th centuries, the sun's central position in our planetary system was accepted fact. But even then, many astronomers believed the sun might be at or near the center of the entire universe, which they thought consisted solely of what we now call the Milky Way galaxy. But as our telescopes grew more powerful and our understanding deepened, we discovered something even more profound and, frankly, more unsettling. In the 1920s, Harlow Shapley used observations of globular clusters to determine that the Sun wasn't at the center of the Milky Way at all, but rather in the outer regions of the galactic disk. Around the same time, Edwin Hubble resolved what had been called spiral nebulae into individual stars, proving they were entire galaxies beyond our own. The Sun isn't the center of anything particularly special. It's just one star among hundreds of billions in a galaxy that itself is just one among hundreds of billions of galaxies spread across unimaginable distances. Each demotion, each step away from centrality, has been met with initial resistance and then reluctant acceptance as the evidence became overwhelming. So where, then, is the center of it all? Where did everything begin? If the universe exploded into existence with the Big Bang 13.8 billion years ago, as decades of observations now confirm, surely there must be a point in space where that explosion occurred. A cosmic ground zero. A place we could point to and say, there, that's where it all started. It seems like a reasonable question, doesn't it? Every explosion we've ever witnessed has an epicenter, a point of origin. Fireworks burst outward from an initial point. A supernova ejects material from the collapsing core of a dying star. Even the explosion of an atomic bomb has ground zero. Surely, the biggest explosion of all, the one that created everything, must have happened somewhere. Today, we're going on a journey to find that center. We'll travel outward from Earth through ever larger structures in the cosmos, from our local galactic neighborhood to the largest structures in the observable universe. We'll explore the cosmic web that connects everything, peer back to the moment of the Big Bang itself, and confront one of the most mind-bending truths modern physics has revealed. The answer to where is the center of the universe is going to challenge everything your intuition tells you about space, time, and existence itself. Because here's the thing that's going to sound absolutely insane until we work through it together. The universe doesn't have a center. At least, not in any way that makes sense to our everyday experience. And the reason why is far stranger and more beautiful than any explanation involving a simple point in space. The center of the universe is everywhere and nowhere all at once. It's here, right where you're sitting. It's in a galaxy 46 billion light years away. It's in every point in space simultaneously. I know that sounds like mystical nonsense. Trust me, by the end of this journey, it's going to make perfect sense. But to understand why the universe has no center, we first need to understand where we actually are in the cosmos. We need our cosmic address. So let's start our journey outward from Earth, through progressively larger scales of structure, until we reach the very edge of what we can observe. Only then can we truly grasp the profound implications of a centerless universe. Let's begin with what we know, what we can see with our own eyes on a clear night far from city lights. We live on Earth, the third planet from a fairly ordinary star we call the Sun. Our Sun is actually quite typical, a main sequence star of spectral type G to V, what astronomers call a yellow dwarf. It's been shining steadily for about 4.6 billion years and has enough fuel to continue for another 5 billion years before it exhausts its hydrogen and begins its transformation into a red giant. Our Sun is one of somewhere between 100 billion and 400 billion stars that make up the Milky Way galaxy. That's a staggering range of uncertainty, isn't it? A factor of 4 uncertainty in the census of our own galaxy. We can count distant galaxies billions of light years away with remarkable precision. We can map the cosmic microwave background with exquisite detail, but we can't get a precise census of our own galaxy because we're inside it, embedded in its disk, trying to see through clouds of dust and gas that obscure our view. It's like trying to count all the trees in a forest while standing in the middle of it, with fog limiting your visibility. The Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped structure made of stars, with spiral arms curling out from the ends of that bar. This bar is relatively recent discovery in galactic astronomy, only definitively confirmed in observations from the Spitzer Space Telescope in 2005. For decades, astronomers debated whether our galaxy had a bar or not. The very structure of our home was unclear to us because of our position within it. If you could somehow float above the galactic plane and look down at it, you'd see a magnificent pinwheel of stars, gas, and dust rotating through space, glowing blue-white along the spiral arms where young, hot stars are actively forming, and yellower in the older, more stable regions like the central bulge and the spaces between the arms. The whole structure spans about 100,000 light years from edge to edge, a distance so vast that light itself, traveling at the ultimate cosmic speed limit, takes 100,000 years to cross it. And it's roughly 1,000 light years thick in the disk, though it bulges significantly in the center where older stars are densely packed. To put this in perspective, if you scaled the Milky Way down so that it was the size of the continental United States, our entire solar system, from the Sun all the way out to the orbit of Neptune, would be about the size of a quarter. And Earth itself would be invisible, smaller than a speck of dust on that quarter. We're located in what's called the Orion Spur, sometimes also called the Orion Arm or the Orion Cygnus Arm, a minor spiral arm between two major arms, the Perseus Arm and the Sagittarius Arm. It's called a spur because it's not one of the main arms of the galaxy, but rather a branch or connection between them, a shorter, less distinct feature in the overall spiral structure. Our position is about 26,000 light years from the galactic center, roughly halfway between the center and the outer edge. We're in the galactic suburbs, you might say, not in the dense, crowded downtown where stars are packed together so tightly that night would never truly come, where the sky would blaze with countless brilliant stars, but not in the sparse outer reaches either, where stars are rare, and the night sky would be darker than we can imagine. It's actually a pretty comfortable location for life to develop. The inner regions have too much radiation from the supermassive black hole at the galactic center, and from frequent supernovae in the densely populated spiral arms. There's also a higher chance of close stellar encounters that could gravitationally disrupt planetary systems. The outer regions, meanwhile, are poor in the heavier elements necessary for rocky planets and complex chemistry, elements that are only created in the cores of massive stars and scattered through space when those stars explode as supernovae. The Sun takes about 225 to 250 million years to complete one orbit around the galactic center. This orbital period is sometimes called a cosmic year or a galactic year, since the Sun formed about 4.6 billion years ago. It has completed roughly 20 orbits of the Milky Way. Every location on Earth has made 20 circuits of the galaxy. The last time we were at this position in our orbit, around 225 million years ago, it was the Triassic period on Earth. Dinosaurs were just beginning to evolve, and the supercontinent Pangaea was still intact. We're moving at a clip of around 220 kilometers per second relative to the galactic center, which is about 492,000 miles per hour. That's fast enough to circle the Earth in less than a minute. But you don't feel any of that motion, just as you don't feel Earth's rotation at over 1,000 miles per hour at the equator, or its orbit around the Sun at over 67,000 miles per hour. Everything in our local neighborhood is moving together, like passengers on a train, all sitting still relative to each other, even as the train hurtles down the tracks. The stars you see in the night sky are all making roughly the same orbital journey around the galaxy that we are, give or take a few tens of kilometers per second of individual motion. Now, the Milky Way doesn't exist in isolation. It's part of a small collection of galaxies called the local group. This is our immediate cosmic neighborhood, the galactic equivalent of your street or block. The local group contains about 80 galaxies spread across a region roughly 10 million light years in diameter. That might sound enormous, and it is by human standards. Every single step you've ever taken, every journey you've made, happens within a region that's incomprehensibly smaller than this 10 million light year distance. But on cosmic scales, it's actually quite compact and cozy. There are much richer galaxy groups and clusters out there containing hundreds or thousands of galaxies in similar sized volumes. The local group is dominated by 3 large spiral galaxies, The Milky Way, our home, with its estimated mass of about 1.5 trillion solar masses, though estimates vary. Andromeda, also known as M31 or NGC 224, which is the largest galaxy in the local group and located about 2.5 million light years from us. Andromeda is massive, perhaps containing up to 1 trillion stars, making it the dominant member of the local group. It's actually visible to the naked eye from Earth on dark nights as a fuzzy patch in the constellation Andromeda, making it the most distant object you can see without a telescope. What you're seeing is light that left that galaxy 2.5 million years ago, when our ancestors on Earth were early hominids just beginning to use stone tools. And Triangulum, also known as M33 or NGC 598, which is a bit smaller than the Milky Way and Andromeda, and about 3 million light years away from us. Triangulum is notable for being the third largest member of the local group, and for having an unusually high rate of star formation for a spiral galaxy. These 3 spirals account for most of the mass in the local group, with Andromeda being the biggest kid on the block, roughly the same size as the Milky Way, or perhaps slightly larger. For a long time, it was thought Andromeda was significantly larger, but recent measurements have suggested the Milky Way might be more massive than previously thought, bringing the 2 galaxies closer to parity. The rest of the local group consists of dozens of smaller dwarf galaxies, many of which orbit around the Milky Way or Andromeda like satellites. These dwarf galaxies come in several types. There are dwarf spheroidal galaxies, which are small, faint, and diffuse, containing mostly old stars. There are dwarf irregular galaxies, which are small but have some ongoing star formation and don't have a regular shape. And there are dwarf elliptical galaxies, which are like miniature versions of the giant elliptical galaxies found in rich galaxy clusters. Some of these dwarfs you might have heard of. The large and small Magellanic clouds, for instance, which are visible from the southern hemisphere as fuzzy patches in the night sky, looking almost like detached pieces of the Milky Way. Ferdinand Magellan's crew observed them during their circumnavigation of the globe in the early 16th century, which is how they got their name, though of course they were known to indigenous peoples of the southern hemisphere for millennia before that. These are small, irregular galaxies. The Large Magellanic Cloud contains maybe 10 billion stars. The Small Magellanic Cloud, even fewer, and they're gravitationally bound to the Milky Way and will likely eventually be consumed by it, adding their stars to our galaxy. In fact, the Milky Way is quite a cannibal. Astronomers have identified several streams of stars in the halo of our galaxy that appear to be the remnants of dwarf galaxies that were tidally disrupted and absorbed in the past. The Sagittarius dwarf elliptical galaxy, for instance, is currently being pulled apart by tidal forces from the Milky Way, leaving long streams of stars wrapping around our galaxy. This process of smaller galaxies being absorbed by larger ones is thought to be one of the main ways that big galaxies like the Milky Way grow over cosmic time. We're built from the accumulated remains of dozens or hundreds of smaller galaxies that wandered too close and were torn apart and incorporated into our structure. Andromeda has its own system of satellite galaxies, at least 14 that have been identified so far, though there are likely more too faint to detect with current technology. M32 and M110 are two dwarf elliptical galaxies that orbit close to Andromeda and are visible in even small telescopes. These satellites are thought to interact with Andromeda in complex ways, possibly triggering bursts of star formation through tidal interactions or being slowly stripped of their stars. Here's something fascinating that transforms our understanding of the local group's future. Andromeda and the Milky Way are actually heading toward each other. Despite the expansion of the universe pushing most galaxies apart, despite the fact that space itself is growing between distant galaxies, we and Andromeda are close enough that our mutual gravitational attraction is stronger than the expansion of space between us. We're approaching each other at about 110 kilometers per second, and in about 4 to 5 billion years, we're going to collide and merge into a single giant elliptical galaxy that astronomers have already affectionately nicknamed Milkomeda, or sometimes Milkdromeda. Don't worry about the collision, though. By that time, the sun will be near the end of its life anyway, having swollen into a red giant and likely consumed the Earth. But even if Earth were still around, the collision wouldn't be catastrophic in the way you might imagine. Galaxies are mostly empty space. The distances between stars are so vast that when two galaxies merge, actual stellar collisions are incredibly rare. The stars would simply pass by each other like two swarms of fireflies interpenetrating on a summer night. The real action would be in the gravitational chaos, stars being flung to new orbits, new bursts of star formation triggered by colliding gas clouds, and the black holes at each galaxy's center eventually spiraling together and merging. This is the scale we're starting from, our local cosmic neighborhood. A small cluster of galaxies, gravitationally bound together, moving through space as a unit. But the local group is just the beginning. It's just one tiny piece of a much larger structure. Zoom out further, and the local group reveals itself to be an outlying suburb of something much more massive, the Virgo Supercluster. This is an enormous collection of galaxy groups and clusters spanning about 110 million light years. It contains around 47,000 galaxies, a number so large it almost loses meaning. How do you wrap your mind around 47,000 galaxies? Each one contains billions or even trillions of stars. Each of those stars potentially hosts planets. The scale becomes almost abstract. At the heart of the Virgo supercluster lies the Virgo cluster itself, a dense concentration of galaxies about 54 million light years from us in the direction of the constellation Virgo. The Virgo cluster contains somewhere between 1,500 and 2,000 galaxies packed into a region about 15 million light years across. At its center sits M87, a giant elliptical galaxy, and one of the most massive galaxies known in our cosmic neighborhood. M87 is famous for hosting a supermassive black hole with a mass of about 6.5 billion times that of the Sun. The very black hole that was photographed in 2019 in that iconic image that showed a glowing ring of matter swirling around a dark center. The Virgo Supercluster isn't a random scattering of galaxies. It has structure, with filaments and sheets of galaxies connecting various clusters and groups. The local group sits on the outer fringes of one such filament, what's called the local sheet, a flattened concentration of galaxies that includes the local group and several other nearby groups. What makes the Virgo Supercluster particularly interesting is that everything within it is moving, and moving in a very specific way. We're all falling towards something, pulled by gravity toward a region of particularly high density. For a long time, astronomers referred to this gravitational focal point as the Great Attractor because its gravitational pull affects the motion of our galaxy and many others around us. It lies about 220 million light years away in the direction of the Hydra Centaurus supercluster, and it's pulling the Milky Way toward it at a velocity of around 600 kilometers per second. The Great Attractor was mysterious for decades because it sits in a part of the sky that's heavily obscured by the plane of our own Milky Way. Imagine trying to see distant city lights through a thick fog. That's what astronomers were dealing with. But as our instruments improved, particularly with observations in wavelength that can penetrate dust better, we began to map the structure of this region. And what we found was that the Great Attractor itself is just part of an even larger structure, a massive concentration of galaxy clusters. Now, here's where it gets even more interesting. For a long time, we thought the Virgo Supercluster was its own discrete structure, a kind of island of galaxies in an expanding ocean of space. But in 2014, a team of astronomers led by R. Brent Tully at the University of Hawaii made a stunning discovery. Using new techniques to map the velocities of galaxies, how fast they're moving, and in what direction, they realized that the Virgo Supercluster is actually just one part of an immensely larger structure. They called it Laniakea. This is where our journey starts to get truly mind-bending, because we're about to step up to a scale where individual galaxies are like grains of sand, and and even galaxy clusters are just small neighborhoods in a sprawling megalopolis. Laniakea. The name means immeasurable heaven in Hawaiian, suggested by Naua Napoleon, an associate professor of Hawaiian language at Cap Iolani Community College. The name honors Polynesian navigators who used knowledge of the heavens to voyage across the immensity of the Pacific Ocean, and it's almost absurdly appropriate for this immense structure. This is our home on the very largest scales that can meaningfully be called a structure. It's the cosmic watershed in which we reside, the basin of gravitational attraction that defines our corner of the universe. Let me try to give you a sense of scale here, though honestly, these numbers are so large they almost lose meaning. Laniakea is approximately 500 million light years across. To put that in perspective, if you could travel at the speed of light, the fastest speed possible in the universe, it would take you 500 million years to cross it. The entire history of complex life on Earth, from the Cambrian explosion to today, is less than 600 million years. You could almost cross Laniakea in the time it took for life on Earth to evolve from simple sea creatures to humans. Laniakea contains the mass of roughly 100 million billion suns. That's 10 to the power of 17 solar masses, one followed by 17 zeros. To put that in more concrete terms, if you took all the matter in our sun and replicated it 100 million billion times, you'd have the mass contained in Laniakea. It encompasses about 100,000 galaxies, 100,000 entire galaxies, each containing billions or trillions of stars. Each of those stars potentially hosting planets spread across this vast structure. The Milky Way, which contains everything we can see with our naked eyes, which contains our entire solar system and hundreds of billions of other star systems, is just one of 100,000 galaxies in Laniakea. The local group, with its 80 galaxies, is an infinitesimal fraction of Laniakea. The Virgo Supercluster, which we once thought was our largest address. All of these are just small components within Laniakea. We sit in the outskirts of it, like someone living in a rural area at the edge of a continental scale watershed. discovery of Laniakea represents a fundamental shift in how we understand cosmic structure. Previous attempts to define superclusters focused on regions of high density, places where galaxies are packed more closely together than average. You'd look at the distribution of galaxies in the sky and in 3 dimensions and try to identify clumps, concentrations where there are more galaxies per unit volume than in surrounding regions. This approach had been used since the 1950s and led to the identification of structures like the Virgo Supercluster, the Coma Supercluster, and others. But this density-based approach has problems. Where exactly do you draw the boundary? How do you decide what density threshold separates a supercluster from the region around it? Different astronomers, using different criteria, would get different results, making comparison difficult. But R. Brent Tully and his colleagues took a completely different approach. They looked at motion, at how galaxies are flowing through space under the influence of gravity. This is a fundamentally different way of defining structure, based on dynamics rather than just spatial distribution. It's like the difference between looking at a map that shows where cities are located versus looking at a map that shows traffic flow patterns. The latter tells you something about how the system actually works, how different parts interact and influence each other. Imagine a landscape after a rainstorm. Water flows downhill, right? Pulled by gravity toward the lowest points. And you can define watersheds, regions where all the water drains toward a common point, often a river or lake. The ridges between watersheds, the high points, are the dividing lines, places where water on one side flows one way toward one river system, and water on the other side flows a different way toward a different river system. If you wanted to map out the watershed structure of a continent, you wouldn't just look at where the land is high or low. You'd look at which way water flows at each point. Laniakea is like a gravitational watershed. It's defined not by where galaxies are, but by where they're going. The boundary of Laniakea marks the divide between regions flowing toward our basin of attraction and regions flowing toward other basins. Using data from thousands of galaxies gathered over decades, including extensive observations from the Green Bank Telescope and other radio observatories, the team mapped out the peculiar velocities of galaxies. This is the motion of galaxies relative to the overall expansion of the universe. As we'll discuss in much more depth later, the universe is expanding, carrying galaxies apart from each other. But superimposed on that expansion are additional motions caused by gravity. A galaxy might be pulled toward a massive cluster, for instance, or pushed away from an underdense region. These gravitational motions are the peculiar velocities. By mapping these peculiar velocities, Tully's team could trace out the flow lines of galaxies, like mapping wind currents or ocean currents. And what they found was beautiful. Galaxies within a certain region all flow inward toward a central basin of attraction. That region is Laniakea. The center of this basin, the point toward which everything is flowing, is the great attractor region that had been identified decades earlier. But now we could see it in context as the gravitational focal point of this immense superstructure. The boundary of Laniakea, the edge of this cosmic watershed, is marked by regions where the flow changes direction. It's like a ridge in our water analogy, a divide where galaxies on one side are flowing into the Laniakea basin, and galaxies on the other side are flowing into a different basin. On the far side of Laniakea's boundary lies the Perseus-Pisces Supercluster in one direction, the Shapley Supercluster in another, the Coma Supercluster in yet another. Each of these is its own basin of attraction, with galaxies flowing toward its center. Now, here's something important to understand about Laniakea. Unlike smaller structures like galaxy clusters, or even the local group, Laniakea is not gravitationally bound. What does that mean? Well, the local group, for instance, is a bound structure. The galaxies in it are gravitationally tied to each other strongly enough that they'll never separate. They're a family unit that will stick together indefinitely, eventually merging into a single large galaxy. Similarly, the Virgo cluster is bound. The galaxies in it are going to stay together. But Laniakea is so large that the expansion of the universe is winning over gravity. Even though galaxies within Laniakea are flowing toward the great attractor right now, they'll never actually get there. The expansion of space is pulling the different parts of Laniakea apart faster than gravity can pull them together. Laniakea is a temporary structure, a pattern that exists now but won't last. Billions of years from now, as dark energy continues to drive the accelerating expansion of the universe, the various parts of Laniakea will be carried away from each other, losing causal contact, disappearing beyond each other's cosmic horizons. There's something almost poignant about that. We exist at a special time in cosmic history when we can still see and map these immense structures. 100 billion years from now, if there are still civilizations around, they'll live in a lonelier cosmos. The only galaxies they'll be able to see will be those in their own local group, everything else having been carried beyond reach by expansion. They'll have no way to know that they live in a much larger universe. They'll think their little cluster of galaxies is all there is. But we're getting ahead of ourselves, because even Laniakea, as immense as it is, isn't the largest structure we can identify. In late 2024, new data revealed something stunning. Laniakea itself appears to be part of an even larger basin of attraction. The Shapley concentration, named after astronomer Harlow Shapley, who first observed it in the 1930s. This is the greatest concentration of matter in our local universe, a massive assemblage of galaxy clusters, and new observations from the Cosmic Flows Project, the same team that mapped Laniakea, suggest that Laniakea is actually flowing toward the Shapley concentration as part of an even larger basin of attraction. This is mind-bending. We're not just moving through space because of the Milky Way's orbit in the local group. And we're not just moving because the local group is falling toward the Virgo cluster. And we're not just moving because everything in this region is falling toward the Great Attractor. We're also, apparently, part of a much grander motion toward the Shapley concentration, which lies about 650 million light years away. The Shapley concentration is about 10 times the volume of Laniakea. 10 times. Let that sink in. Laniakea contains 100,000 galaxies and spans 500 million light years. And it's just one component in something 10 times larger. The Shapley concentration may contain 1 million galaxies, maybe more. The numbers start to become almost meaningless at this scale. How do you conceptualize a million galaxies, each one an island universe of billions of stars, many with planets, some perhaps with life, all bound together in this incomprehensibly vast structure? Now, here's where we need to be careful. The Shapley concentration being larger than Laniakea doesn't necessarily mean it's a higher level structure in some hierarchical sense. In fact, modern cosmology is moving away from thinking about the universe as neatly organized into hierarchical levels. Instead, we're recognizing that cosmic structure is more like a complex web or network, with regions of high and low density interconnected in intricate ways. Which brings us to the largest scale of structure that exists in the universe, a scale at which all the structures we've discussed so far, the local group, the Virgo Supercluster, Laniakea, the Shapley concentration, all become just small features in a grand cosmic tapestry. I'm talking about the cosmic web. If you could somehow step outside the universe and look at it from a truly God's eye view, what you'd see would look almost organic, like the structure of a sponge or the neural networks in a brain, or the mycelium network of a fungus spreading through soil. This is the cosmic web, the largest scale structure in the universe. The cosmic web consists of four main components. First, there are filaments, long, thread-like structures of galaxies, and dark matter stretching for hundreds of millions of light years through space. These filaments are the highways of the cosmos, channels along which galaxies are strung like beads on a string. They contain the majority of the matter in the universe and are where most galaxies reside. Second, there are nodes, dense regions where multiple filaments intersect. These nodes are the sites of massive galaxy clusters, the largest gravitationally bound structures in the universe. Places like the Virgo cluster or the Coma cluster, where thousands of galaxies are concentrated in a relatively small volume of space. These are the crossroads of the cosmic web, the metropolitan centers where all the highways meet. Third, there are walls or sheets, flattened regions where multiple filaments merge together. These are like vast two-dimensional surfaces stretching through space, with galaxies concentrated along them. Some of these walls are truly enormous. The Sloan Great Wall, for instance, which was discovered in 2003 and stretches for about 1.4 billion light years, making it one of the largest single structures ever identified. And fourth, there are voids, enormous regions of space that are relatively empty of galaxies. These voids are like the bubbles in a foam or the air spaces in a sponge. They're huge, typically 300 to 1,000 million light years across, and they contain very few galaxies, just the occasional lonely galaxy wandering through the emptiness. About 70% of the universe's volume is in these voids, even though they contain only about 15% of the matter. The cosmic web isn't static. It's a structure that formed over billions of years through the action of gravity on the initial density fluctuations present in the early universe. In the first moments after the Big Bang, the universe was incredibly smooth and uniform, but not perfectly so. There were tiny ripples in the density of matter. Some regions were ever so slightly more dense than average, others ever so slightly less dense. Over time, gravity amplified these differences. The slightly denser regions attracted more matter, becoming denser still. The slightly less dense regions lost matter to the denser regions, becoming even emptier. This process, called gravitational instability, is the engine that drives structure formation in the universe. It's a runaway process. The rich get richer, and the poor get poorer, cosmologically speaking. But the formation of structure isn't uniform in all directions. It's anisotropic, meaning it happens at different rates in different directions. This is because of something called the Seldovich approximation, named after the Russian physicist Yakov Seldovich, who worked out the mathematics in 1970. Seldovich showed that gravitational collapse happens faster along one direction than another, leading to the formation of elongated structures like filaments rather than spherical structures. Here's a way to visualize it. Imagine you have a cloud of gas in space. Gravity is pulling on it, trying to make it collapse. If gravity were perfectly symmetric in all directions, the cloud would collapse into a sphere. But gravity isn't perfectly symmetric because the distribution of matter around the cloud isn't perfectly symmetric. Maybe there's more matter on one side than another. So the cloud starts to collapse more quickly along one axis than another. It becomes flattened like a pancake. This is a sheet. Then, as collapse continues, it collapses more along a second axis, becoming elongated. This is a filament. Only at the very end, at the nodes where filaments intersect, does collapse happen in all three directions, forming dense clusters. This is the Zeldovich pancake scenario, and it beautifully explains the structure we see in the cosmos. The universe didn't form galaxies and then group them into clusters, and then group clusters into superclusters. Instead, large-scale structure formed first. The filaments and sheets and galaxies formed within those structures. The cosmic web came first, and galaxies are just the visible tracer of its invisible dark matter scaffolding. Dark matter, that mysterious substance that makes up about 85% of the matter in the universe, but doesn't interact with light or normal matter except through gravity, is crucial to all of this. The filaments and walls of the cosmic web are primarily dark matter. The galaxies we see are like lights tracing out the structure of an invisible framework. Dark matter collapsed first, creating gravitational wells, and normal matter, the stuff we can see, fell into those wells and formed galaxies and stars. Computer simulations of cosmic structure formation, like the Millennium simulation or the more recent Illustris TNG project, can model this process from shortly after the Big Bang all the way to the present day. These simulations start with the tiny density fluctuations we observe in the cosmic microwave background radiation. That's the afterglow of the Big Bang, and they let gravity do its work. And what emerges from these simulations looks remarkably like the real universe. They produce cosmic webs with filaments, nodes, walls, and voids. They produce galaxies that form and evolve in realistic ways. The agreement between simulation and observation is actually kind of stunning, and it gives us confidence that we understand the basic physics of structure formation. Recent observations with instruments like the EROSITA X-ray telescope have even been able to detect the hot gas that fills the filaments of the cosmic web. This is the warm, hot intergalactic medium, or WIM, gas heated to temperatures between 100,000 and 10 million degrees Celsius. It's thought that about half of the normal matter in the universe is tied up in this warm, hot phase, residing in the filaments between galaxies. It's incredibly diffuse, less than 100 hydrogen ions per cubic meter, but it's there, filling the vast spaces between the bright nodes of galaxy clusters. So that's the cosmic web, the largest scale structure in the universe. Filaments stretching across hundreds of millions of light years, connecting dense nodes of galaxy clusters with vast voids in between. It's a structure that's at once regular enough to be scientifically described. There are statistical patterns we can measure and model, but also complex and irregular enough to be endlessly interesting. No two parts of the cosmic web are exactly alike. Now, here's the key question. We've journeyed outward from Earth to the Milky Way, to the local group, to the Virgo Supercluster, to Laniakea, to the Shapley concentration, to the cosmic web. At each step, we found larger and larger structures, but we've never found a center. The Milky Way doesn't have a center that's special for the universe. It just has a center for itself. The local group doesn't sit at the center of the Virgo supercluster. The Virgo supercluster doesn't sit at the center of Laniakea, and Laniakea doesn't sit at the center of anything larger. In fact, the cosmic web doesn't have a center at all. It's the same everywhere, statistically. If you picked a random spot in the universe and looked around on scales of hundreds of millions of light years, you'd see filaments, nodes, walls, and voids in roughly the same proportions as anywhere else. There's no central hub, no downtown of the universe where everything is denser or brighter or more important. It's homogeneous, the same everywhere on large scales. But wait, you might be thinking, we've been talking about the structures we can see. Surely there are structures beyond what we can observe. Maybe the center is just too far away for us to see. To address that, we need to talk about the observable universe and why it has a very definite boundary. Right now, at this moment, the most distant thing you could theoretically see with a perfect telescope is about 46.5 billion light years away in terms of proper distance. Wait, hold on. How can we see something 46.5 billion light years away when the universe is only 13.8 billion years old? Shouldn't the most distant thing we can see be 13.8 billion light years away? Since that's how long light has had to travel, this seems like a direct contradiction. How can light from something 46 billion light years away reach us if light has only had 13.8 billion years to travel? At the speed of light, it should only be able to cover 13.8 billion light years, right? This is one of the most common points of confusion in cosmology, one that trips up even scientifically literate people. And it's worth taking the time to understand it properly, because it gets at the heart of what we mean by distance in an expanding universe. The answer involves understanding that space itself has been expanding while light was traveling toward us, fundamentally changing what we mean by distance. Let's work through this carefully with a specific example. Imagine there's a galaxy that emitted light 13.7 billion years ago, very shortly after the Big Bang, when the universe was only about 100 million years old. That light has been traveling toward us for 13.7 billion years, almost the entire age of the universe. You might think that means the galaxy is 13.7 billion light years away. After all, the light traveled for that long at the speed of light, so shouldn't it have covered that distance? But you'd be wrong, and here's why. While that light was traveling toward us, space itself was expanding. The galaxy wasn't sitting still in space, waiting for its light to reach us. It was being carried away from us by the expansion of space itself. Think of it this way. Imagine an ant walking across a rubber band that's being stretched. The ant walks at 1 centimeter per second toward one end of the band. In a normal, non-stretching band, the ant would cover 1 centimeter every second and would reach the end in a predictable time. But if the band is being stretched while the ant walks, the ant still moves at 1 centimeter per second relative to the rubber directly beneath its feet. But the destination is getting farther away, even as the ant walks toward it. That's what happened to the light from that distant galaxy. The light moved at the speed of light. Obviously, that's the only speed light can move at. But while it was in transit, the space it had already crossed was expanding behind it, and the space it still had to cross was expanding in front of it. The galaxy itself was being carried farther and farther away by this expansion. By now, 13.7 billion years later, that galaxy is not 13.7 billion light years away from us. It's about 46 billion light years away. The space between us and that galaxy has stretched enormously during the time the light was traveling. To understand this more precisely, we need to distinguish between three different kinds of distance that cosmologists use when talking about the universe. First, there's light travel distance, sometimes called look-back time distance. This is simply how long the light has been traveling times the speed of light. For our example galaxy, whose light has been traveling for 13.7 billion years, the light travel distance is 13.7 billion light years. This tells us how far in the past we're seeing the galaxy. It's an indication of time rather than current spatial separation. Second, there's angular diameter distance, which is related to how large an object appears on the sky. This is important for cosmologists calculating the sizes of objects at different distances. But it's not what people usually mean when they ask about distance. Third, and most relevant for our discussion, there's proper distance, also called comoving distance. This is the actual distance to the object right now, at this moment in cosmic time, taking into account all the expansion of space that's occurred since the light was emitted. When we say the observable universe has a radius of 46.5 billion light years, we're talking about proper distance. That's the actual distance, measured at this instant, to the furthest objects whose light has reached us. So, how do we calculate this proper distance? It requires understanding the history of cosmic expansion. The universe hasn't been expanding at a constant rate. In the very early universe, during the first fraction of a second, there's thought to have been a period of exponential expansion called cosmic inflation, where the universe grew by an enormous factor in an incredibly short time. Then, after inflation ended, the expansion slowed down. For the first several billion years of cosmic history, the expansion was decelerating, slowing down due to the gravitational pull of all the matter in the universe trying to pull itself back together. Then, remarkably, about 7 to 8 billion years ago, something strange happened. The expansion started accelerating again, speeding up instead of slowing down. This acceleration is attributed to dark energy, that mysterious component making up 68% of the universe that acts like anti-gravity, pushing space to expand faster and faster. Because of this complex history, the complicated interplay of early rapid inflation, then prolonged deceleration, then acceleration again, the relationship between light travel time and proper distance is definitely not simple or linear. It's not as simple as distance equals velocity times time. Instead, you have to integrate the expansion rate over the entire history of the light's journey, taking into account how fast space was expanding at each moment. The expansion rate is characterized by something called the Hubble parameter, which varies with time. In the early universe, the Hubble parameter was much larger, meaning space was expanding faster. As the universe aged and expansion decelerated, the Hubble parameter decreased. Then, as dark energy took over and expansion began accelerating, the Hubble parameter began increasing again. When you work through all the mathematics of cosmic expansion, carefully integrating the scale factor over time, and taking into account the changing expansion rate based on our best measurements of the universe's composition, the density of matter, the density of dark energy, the curvature of space, you get that 46.5 billion light years number for the current proper distance to the edge of the observable universe. The edge of the observable universe is marked by the surface of last scattering. This is the point in the early universe, about 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this moment, the universe was a hot, ionized plasma, opaque to light. Photons couldn't travel very far before being scattered by free electrons. It was like trying to see through a dense fog. But once neutral atoms formed, the fog cleared. The universe became transparent to light. The light emitted from this surface of last scattering has been traveling through space ever since, redshifted by the expansion of the universe from visible light all the way into the microwave part of the spectrum. This is the cosmic microwave background radiation, or CMB, the oldest light in the universe. When we observe the CMB, we're looking at the surface of last scattering, the edge of the observable universe. We can't see beyond it because the universe was opaque before it. The CMB is remarkably uniform. Its temperature is 2.7 Kelvin in every direction we look, with variations of only about 1 part in 100,000. This uniformity is crucial evidence for something we'll discuss shortly: the cosmological principle, the idea that the universe is the same everywhere on large scales. Now, the observable universe, this sphere of 93 billion light years in diameter centered on us, is just the part of the universe we can see. The actual universe, the whole universe, is likely much larger. How much larger? We don't know. It could be just a bit larger than the observable universe. It could be millions of times larger. It could be infinite. We simply don't know, and may never be able to know with certainty. What we do know is that the observable universe is expanding. Not the universe itself. That's been expanding since the Big Bang. But specifically, what we can observe is growing over time. Every second, light from more distant regions reaches us for the first time. Our cosmic horizon expands by 3 light seconds every second. The distance light travels in that time. So over the course of a year, we can see about 1 light year farther in every direction than we could the year before. But here's the cruel twist. Even though our observable universe is expanding, allowing us to see more and more of the cosmos, the accelerating expansion of the universe is making much of what we can see now forever unreachable. There's a boundary called the cosmic event horizon, beyond which galaxies are receding from us faster than the speed of light due to the expansion of space. We can still see these galaxies, We can see the light they emitted in the past, but we can never reach them. Even traveling at the speed of light, we could never catch up to them because the space between us and them is expanding faster than we can cross it. Currently, the cosmic event horizon is about 16 billion light years away in proper distance. Galaxies beyond that, even though we can see them now, are forever beyond our reach. And as dark energy continues to drive accelerating expansion, more and more of the currently visible universe will slip beyond this horizon. Billions of years from now, all the galaxies outside our local gravitationally bound group will have disappeared beyond the cosmic event horizon. Future civilizations will see a much emptier cosmos than we do. So we have this observable universe, a sphere centered on us, extending 46.5 billion light years in every direction. And within that sphere, we see the cosmic web, filaments and voids and clusters of galaxies distributed uniformly on the largest scales. But crucially, we don't see a center. We don't see a point where things are denser or from which everything appears to be expanding. Every direction looks basically the same. And that's the key to understanding why the universe doesn't have a center. But to really grasp this, we need to go back to the beginning. We need to understand what the Big Bang actually was, and more importantly, what it wasn't. Here's what the Big Bang was not, and this is absolutely crucial to understand. It was not an explosion of matter into empty space from a single point. That's the image most people have, and it's reinforced by almost every popular depiction of the Big Bang you've ever seen. Documentaries show it as a kind of cosmic firecracker going off, a bright point expanding outward, blasting matter and energy out into a pre-existing void. Science fiction and even some educational materials perpetuate this misconception. But that's completely, fundamentally wrong. If the Big Bang had been an explosion in that sense, an explosion of stuff into space, there would be a center, the point where the explosion occurred, the location of the cosmic firecracker before it went off. And if we looked out into space, we should see different things in different directions based on our position relative to that center. In an ordinary explosion, you can tell where the center is by looking at the pattern of the explosion. If you're at the center, you see material rushing away from you in all directions equally. If you're off to the side, you see material approaching from one direction, the direction toward the center, and moving away in the opposite direction. The material is denser in some directions than others. There's an asymmetry that points back to the origin. Similarly, if the Big Bang had been a conventional explosion, there would be an edge to the explosion in some directions, a boundary where the expanding matter meets the empty space beyond. We should be able to look in one direction and see the edge of the universe, the frontier of the explosion. But that's not what we see at all. In every direction we look, we see galaxies extending as far as we can see, with no edge, no boundary, no indication of a preferred direction or center. So, what was the Big Bang? Let's be very precise about this. The Big Bang was the beginning of the expansion of space itself, not an explosion in space, but an explosion of space. Not things moving through space, but space itself coming into existence and growing, stretching, expanding. This is a fundamentally different phenomenon than anything we experience in everyday life, which is why it's so hard to visualize or intuit. Space itself, the three-dimensional fabric in which all events occur, came into existence at the Big Bang. Or if space already existed in some sense. And here we're getting into deep philosophical and physical territory that's honestly still not fully understood. It was compressed to an infinitesimal size, essentially 0 volume, and then began expanding. Before the Big Bang, in the Standard Model at least, there was no space and time. The concepts of before and somewhere else don't even make sense because time and space are things that exist within the universe, not outside it. Asking what came before the Big Bang is like asking what's north of the North Pole. The question contains a category error. It applies a concept, beforeness, that doesn't have meaning in that context. At or arbitrarily close to the moment we call the Big Bang, at what physicists call T equals 0, all of space, possibly infinite space, though this is debated, was compressed to essentially 0 size. The distance between any 2 points was 0. Then it started expanding, and it's been expanding ever since, growing larger and larger, with the distance between any 2 points increasing over time. Here's the key insight that's hard to wrap your head around, and I want to say this as clearly as possible. The Big Bang didn't happen at a location in space. It happened at all locations in space simultaneously. It wasn't an event that occurred somewhere and then spread outward. It was an event that occurred everywhere at once. Every point in the universe today, Earth, the center of the Andromeda galaxy, a 0.46 billion light years away in the direction of the constellation Hydra, another 0.46 billion light years away in the opposite direction. All of these points, all locations in the universe, were in the same place at the moment of the Big Bang. Or more precisely, the distance between any 2 of these points was 0. Let me give you a mathematical way to think about this that might help. Imagine you have a grid of points in space, like a 3-dimensional coordinate system extending infinitely in all directions. Now imagine that the spacing between the points, the distance from one point to the next, is controlled by a factor we'll call AT, the scale factor, which is a function of time. When AT equals 1, the distances are what we'd call normal. They're the distances we measure today. When AT equals 2, all distances are doubled. Every meter becomes 2 meters. Every light year becomes 2 light years. The distance from Earth to the Andromeda galaxy doubles. The distance between atoms in your body would double, though in practice, this doesn't happen because electromagnetic and nuclear forces hold atoms together and resist the expansion. When AT equals 1/2, all distances are halved. The expansion of the universe is described by this scale factor increasing over time. As time goes forward from the Big Bang to today, AT grows from 0 to 1. As it grows, all distances between points grow proportionally. A distance that was 1 million light years when AT was 0.5 becomes 2 million light years when AT is 1. This is why we see distant galaxies moving away from us. The space between us and them is growing. Now rewind time, go backwards toward the Big Bang. The scale factor AT gets smaller. Distances shrink. the space between galaxies shrinks. The size of the observable universe shrinks. Eventually, at the moment of the Big Bang, at t equals 0, the scale factor AT reaches 0. All distances are 0. Every point in space is coincident with every other point. The entire universe, possibly infinite in extent, is compressed to a single point, or more accurately, to 0 size. This is the Big Bang singularity, a moment when the mathematics of general relativity breaks down and physical quantities like density and temperature become infinite, or at least ill-defined. Now run time forward from that moment. The scale factor starts increasing from 0. Distances between points start growing. Space is expanding. Matter and energy, which were compressed to infinite density, spread out as the space they occupy grows. But notice, and this is absolutely critical, there's no center to this expansion. If you sit at any point in this expanding grid and look around, you see all the other points moving away from you. The farther away a point is, the faster it recedes, because there's more expanding space between you and it. And here's the kicker. Someone sitting at any other point would see exactly the same thing. They would see all points moving away from them, with more distant points receding faster. Everyone sees themselves at the center of the expansion, which means no one is actually at the center. There is no center. This is fundamentally, categorically different from an ordinary explosion. In an ordinary explosion, which we're all familiar with from fireworks to bomb blasts to supernovae, there's a central point where the explosion occurred. Material, matter, energy expands outward from that point into surrounding space. The space itself already exists and doesn't change. The explosion happens in space. If you were sitting at the center of the explosion, at the exact point where the bomb went off, you'd see material rushing away from you in all directions at high speed. Everything would be receding from you radially outward. But if you were off to the side, away from the center, your experience would be completely different. You'd see the explosion rushing past you. Material on the side closer to the center would be moving toward you. Material on the far side would be moving away. Some material might even be moving perpendicular to your line of sight to the center. You'd have a clear, unambiguous sense of direction toward or away from the center. If you tracked the motion of all the material backward in time, the trajectories would converge on a single point, the center. You could point to that spot and say, there, that's where it happened. But in the Big Bang, this is not the case. There is no such preferred direction. From every point, the expansion looks the same. Every observer, no matter where they are in the universe, sees all other points receding from them according to the same law, Hubble's law, which states that recessional velocity is proportional to distance. An observer on a galaxy 10 billion light years away sees the same pattern we do. They see us receding from them. They see another galaxy 10 billion light years away on their other side, also receding from them. If they measured the expansion rate, they'd get the same Hubble constant we measure. They'd calculate the same age for the universe. This is because the Big Bang wasn't stuff moving through space. It's space itself that's expanding, carrying the stuff, the galaxies, the matter with it. Galaxies aren't moving through space in the sense of expansion. They're not traveling from one location to another within a fixed space. Rather, they're largely stationary within their local region of space, and it's the space between them that's growing. They're being carried along as space expands, like raisins in rising bread dough. The dough, space, expands, and the raisins, galaxies, get farther apart. But the raisins themselves aren't moving through the dough. The classic analogy is a balloon with dots marked on it. And it's worth spending a moment really understanding this analogy because it captures something profound. Imagine you take a balloon and mark dots on its surface with a marker before you inflate it. These dots represent galaxies. Now, as you inflate the balloon, what happens? The dots move apart from each other. If you were a tiny two-dimensional being living on the surface of that balloon, standing on one of those dots, you would see all the other dots moving away from you in all directions. And here's the crucial part. The farther apart two dots are, the faster they move apart, because there's more balloon surface between them to expand. A dot that's twice as far away moves apart twice as fast. This is precisely what we observe with galaxies. the farther away a galaxy is from us, the faster it's receding. This relationship is Hubble's law, and it's a direct consequence of the uniform expansion of space. The recessional velocity equals the Hubble constant times the distance. For nearby galaxies, a few million light years away, the recession is slow, maybe a few hundred kilometers per second. For galaxies hundreds of millions of light years away, the recession is much faster, tens of thousands of kilometers per second. For the most distant galaxies we can see, those whose light has been traveling for most of the age of the universe, the recession rate is approaching the speed of light. And for galaxies beyond our cosmic horizon, those whose light hasn't reached us yet or never will, the recession rate exceeds the speed of light. Though this doesn't violate relativity because it's space expanding, not the galaxies moving through space faster than light. But you might object, and this is a common and reasonable objection. The balloon analogy has a center. It's the center of the balloon, the point inside it that everything is expanding away from, the point where you're blowing air in. Doesn't that contradict what I just said about there being no center? The key, and this is subtle, is that in the balloon analogy, we're supposed to imagine ourselves as two-dimensional beings living on the surface of the balloon. We exist only on that surface, confined to it, unable to perceive or access any third dimension. From that perspective, from within the two-dimensional surface universe, there is no center. The surface of the balloon is uniform. It curves back on itself, and every point on it looks like every other point. Pick any dot on the balloon's surface, and you're at the center of your observable surface universe. The three-dimensional center of the balloon, that point in the middle where the air is not part of the two-dimensional surface universe. It's in a direction that doesn't exist for beings confined to the surface, a direction perpendicular to the only two dimensions they can perceive or move through. Similarly, our three-dimensional universe might be curved in some higher dimensional space that we can't perceive or access. And there might be a center in that higher dimension, in some fourth or fifth spatial dimension beyond our three. But from within our three-dimensional space, there is no center we can identify or locate or travel to. Every point is equivalent. This gets at something profound about the geometry of space, the possibility that our three-dimensional space is curved in ways we can't directly perceive. Because the curvature is in dimensions we don't have access to. But for our purposes, the key takeaway is simple and clear. The Big Bang happened everywhere at once. There is no point in our three-dimensional space where it occurred. There is no center to the universe within the universe itself. Let me be very clear about what the cosmic microwave background tells us. The CMB is light from 380,000 years after the Big Bang, from the surface of last scattering. When we look at the CMB, we're looking back in time to that early epoch. And crucially, we see it coming from all directions equally. The CMB surrounds us in a perfect sphere. This tells us that the Big Bang happened equally in all directions from us. Or more accurately, it tells us that 380,000 years after the Big Bang, the universe was nearly perfectly uniform in all directions from the point in space where we are now. If the Big Bang had been an explosion from a single point, we would see the CMB coming from only one direction, the direction toward that point. Instead, we see it from all directions because the early universe was everywhere. The hot, dense conditions of the early universe existed at every point in space, not just at some central location. This is the profound truth that modern cosmology has revealed. The universe doesn't have a center because the Big Bang didn't have a center. It happened everywhere at once, and every point in the universe has an equal claim to being the center of the expansion. This brings us to one of the most important principles in all of cosmology, the cosmological principle. It states that on large enough scales, the universe is homogeneous and isotropic. Homogeneous means it's the same everywhere. No point in space is special. Isotropic means it looks the same in all directions. No direction is special. Now, this is clearly not true on small scales. The universe around you is not homogeneous. You're on Earth, which is very different from the space between Earth and the Moon, which is very different from the Sun, which is very different from the empty space between stars. There's structure everywhere everywhere you look. Planets, stars, galaxies, clusters. But on very large scales, scales of hundreds of millions of light years, all that structure averages out. When you look at volumes of space that large, they all have roughly the same average density of matter and the same average number of galaxies. The cosmological principle is both a philosophical statement and an empirical observation. Philosophically, it's an extension of the Copernican principle, the idea that we don't occupy a special place in the universe. Copernicus demoted Earth from the center of the solar system. Later observations demoted the solar system from any special location in the Milky Way, and the Milky Way from any special place among galaxies. The cosmological principle extends this to the ultimate conclusion. Not only are we not special locally, but no place in the universe is special. Every observer, no matter where they are, should see the same large-scale structure. Empirically, the cosmological principle is supported by multiple lines of evidence. First, the cosmic microwave background. As I mentioned, the CMB is extraordinarily uniform. Its temperature varies by only about 1 part in 100,000 across the sky. This tells us that the early universe was extremely smooth and homogeneous. If there had been significant large-scale asymmetries or a preferred direction, we would see them imprinted in the CMB. Second, galaxy surveys. When astronomers map the positions of millions of galaxies across large volumes of space, they find that while their structure on intermediate scales, filaments and voids and clusters, the distribution becomes more and more uniform as you look at larger and larger volumes. On scales above about 600 million light years, the universe appears to be statistically homogeneous. The density of galaxies averages out to the same value everywhere. Third, Hubble's law. The observation that the recessional velocity of galaxies is proportional to their distance. Farther galaxies recede faster is exactly what you'd expect from a uniform expansion. If the expansion were not uniform, if some regions were expanding faster or slower than others, we'd see deviations from Hubble's law. The fact that Hubble's law holds to great accuracy in all directions tells us that the expansion is the same everywhere, supporting isotropy. Now, I should mention that the cosmological principle, like any scientific principle, is continually being tested and refined. There have been observations that seem to challenge it, at least in subtle ways. Some very large structures have been found that seem to violate expectations based on the principle. The Sloan Great Wall, for instance, stretches for 1.4 billion light years, which is larger than what most models predict should exist if the universe were perfectly homogeneous. There have also been claims of anomalies in the cosmic microwave background. The so-called cold spot, a region of the CMB that's unusually cold compared to its surroundings. The axis of evil, an unexpected alignment in the pattern of fluctuations in the CMB. Some researchers have argued that these anomalies hint at violations of isotropy, suggesting that the universe might have a preferred direction or axis. Additionally, there's the Hubble tension, a discrepancy between two different methods of measuring the expansion rate of the universe. One method uses the CMB and the cosmological principle to extrapolate the expansion rate. Another method uses nearby supernovae and galaxies to measure it directly. The two methods give values that differ by about 9%, which is more than can be explained by measurement error. Some cosmologists have suggested that this tension might indicate that the universe is not as homogeneous as we thought, that perhaps we're in a region that's expanding at a different rate than the average. But despite these potential challenges, the cosmological principle remains our best working hypothesis. The anomalies might be statistical flukes, or they might point to interesting new physics. But the overwhelming weight of evidence still supports the idea that the universe is homogeneous and isotropic on the largest scales. And if the cosmological principle is correct, it has a profound implication. It means that the universe looks basically the same from every vantage point. An alien astronomer in a galaxy 40 billion light years away would see a cosmic microwave background that looks just like ours. They would map filaments and voids in their local cosmic web that looks statistically similar to ours. they would derive the same cosmological parameters, the same age of the universe, the same composition of matter and energy. And crucially, they would see themselves at the center of an observable universe, just like ours. From their perspective, they would be surrounded by galaxies receding in all directions, with the CMB forming a sphere around them at the edge of what they can observe. Just as we see ourselves at the center of our observable universe. This is the key to understanding why the universe has no center. Everyone is at the center of their own observable universe, which means no one is actually at a special central location. The center is everywhere and nowhere. Think about it this way. Imagine you're on the surface of the earth. You can see to the horizon in all directions, and that horizon forms a circle centered on you. You appear to be at the center of a circular region of Earth's surface, but you're not actually at the center of the Earth. You're just at the center of the part you can see. Someone else on the other side of the planet would also see themselves at the center of a circular region. Everyone is at the center of their own visible horizon, but no one is at the center of the whole Earth. The observable universe is just like that horizon. It's the limit of what we can see, not the edge of what exists. And just as the Earth doesn't have a center on its surface, every point on a sphere is equivalent. The universe doesn't have a center in three-dimensional space. This is fundamentally different from older models of the universe. In a geocentric model, Earth was at the center, and everything revolved around it. In a heliocentric model, the Sun was at the center of the solar system. Even in the early 20th century, before Hubble discovered that other galaxies exist, some astronomers thought the Milky Way might be the entire universe, which would make its center the center of everything. But the modern cosmological picture is radically different. There is no center, not even conceptually. The universe is either infinite, in which case an infinite space can't have a center, or it's finite but unbounded, like the surface of a sphere, in which case every point is equivalent and there's no center. This has been one of the hardest concepts for people to accept, including scientists. Einstein himself initially resisted the idea of an expanding universe, even though it was a solution to his own equations of general relativity. He added a cosmological constant to his equations, a kind of anti-gravity term, to keep the universe static. He later called this his biggest blunder when Hubble's observations of galactic redshifts confirmed that the universe was indeed expanding. But the expanding, centerless universe is now firmly established, and it's expanding faster and faster, driven by something we call dark energy. In 1998, two teams of astronomers studying distant supernovae made a shocking discovery. They were measuring the expansion rate of the universe at different epochs by observing type Ia supernovae, which are excellent standard candles because they all have roughly the same intrinsic brightness. By comparing how bright these supernovae appear to how bright they should be based on their distance, the teams could measure the expansion rate of the universe when that light was emitted. What they expected to find was that the expansion was decelerating, slowing down over time due to the gravitational pull of all the matter in the universe. What they actually found was that the expansion is accelerating, speeding up. Distant supernovae were dimmer than expected, meaning they were farther away than they should be if the expansion had been decelerating. The universe wasn't just expanding, it was expanding faster and faster. This discovery was so unexpected, so contrary to everything that was thought to be the case, that both teams initially assumed they had made an error. They double-checked their data, looked for systematic errors, tried to find anything that could explain away the result. But the data held up. The universe really is accelerating. The discovery was awarded the Nobel Prize in Physics in 2011. To explain this acceleration, physicists have invoked something called dark energy. We don't know what dark energy actually is. It's one of the biggest mysteries in modern physics, but we know it's there, and we know roughly how much of it there is, because we can measure its effects on the expansion rate. Dark energy makes up about 68% of the total energy density of the universe. That means more than 2/3 of everything that exists is something we don't understand at all. Dark matter, that other mysterious component, makes up about 27%. Normal matter, the stuff that makes up stars, planets, gas, dust, and us, accounts for only about 5%. We're a tiny minority in a universe dominated by things we can't see and don't fully comprehend. Dark energy acts like anti-gravity. While normal matter and dark matter pull things together through gravity, dark energy pushes space to expand faster. On small scales, like within galaxies, or even within galaxy clusters, gravity is strong enough to overcome dark energy. These structures remain gravitationally bound. But on larger scales, dark energy dominates, driving the accelerating expansion. The simplest explanation for dark energy is that it's a property of space itself, a kind of inherent energy that empty space possesses. This is equivalent to the cosmological constant that Einstein added to his equations. If space has a constant energy density and space is expanding, then the total amount of dark energy in a given volume increases as that volume grows. This leads naturally to accelerating expansion. But there are other possibilities. Dark energy might not be constant. It might change over time. It might be a new kind of field, similar to the fields that describe other forces in physics. Or it might be a sign that our understanding of gravity is incomplete, that general relativity needs to be modified on cosmic scales. We simply don't know yet. Figuring out the nature of dark energy is one of the major goals of modern cosmology. What we do know is that dark energy has profound implications for the future of the universe. If dark energy remains constant or grows stronger, the accelerating expansion will continue indefinitely. Eventually, all the galaxy clusters outside our local gravitationally bound group will be carried beyond our cosmic horizon. Billions of years from now, observers in the Milky Way, assuming any are still around, will see a nearly empty sky. Just the merged remnant of the Milky Way and Andromeda, and a few dwarf galaxies, all slowly dying as their stars burn out. Trillions of years in the future, even stars will cease to form as gas is dispersed and used up. The universe will become dark, filled with dead stellar remnants, black dwarfs, and neutron stars, and black holes. Eventually, even black holes will evaporate through Hawking radiation, though this takes an incomprehensibly long time, 10 to the power of 100 years for the most massive ones. The ultimate fate is a cold, dark, nearly empty universe, still expanding, still accelerating, but essentially dead. It's called the Big Freeze or heat death, the inevitable consequence of entropy and expansion. But this is so far in the future that it's almost abstract, timescales longer than most people can meaningfully think about. For now, we live in a universe that's structurally interesting. Dark energy is accelerating expansion, yes, but it hasn't yet pulled everything apart. We can still see the cosmic web, map superclusters, study distant galaxies. We live in what you might call the golden age of cosmic structure, after the era of initial formation, but before the era of disintegration. And throughout all of this expansion, accelerating or otherwise, there remains no center. Dark energy doesn't push things away from a central point. It uniformly increases the expansion rate everywhere. Every point in space sees the same effect, the same acceleration. The centerless nature of cosmic expansion is preserved. But is the universe really perfectly homogeneous and isotropic? Are there really no special locations or directions? As I mentioned earlier, there have been a few observations that seem to hint at violations of the cosmological principle. Things that wouldn't exist if the universe were truly uniform on the largest scales. Let's talk about some of these anomalies. First, there's the cold spot in the cosmic microwave background. The CMB, as I've said, is remarkably uniform, but there are tiny fluctuations in temperature, hot spots, and cold spots that represent slightly denser and slightly less dense regions in the early universe. Most of these fluctuations are small and randomly distributed. But there's one region, about 5 degrees across on the sky, that's significantly colder than average. It's about 70 microkelvins colder than the surrounding regions. This cold spot was first identified in data from the WMAP satellite and confirmed by the Planck satellite. It's statistically unusual, not impossible, but unlikely enough to raise eyebrows. Various explanations have been proposed, It could be a statistical fluke, just a rare, random fluctuation. It could be caused by a supervoid, an enormous underdense region between us and the surface of last scattering, though this explanation has been controversial. Or it could be something more exotic, perhaps a signature of a collision between our universe and another bubble universe in a multiverse, though this is highly speculative. Then there's the axis of evil. This is a somewhat tongue-in-cheek name for an observed alignment in the pattern of temperature fluctuations in the CMB. When you analyze the CMB, you can break down the pattern of fluctuations into components at different angular scales, a bit like doing a Fourier transform. The largest scale components, the quadrupole and octupole, seem to be aligned with each other and with the plane of the solar system. This is weird because there's no reason the CMB should have any relationship to the orientation of our solar system. The solar system formed billions of years after the light of the CMB was emitted, and it's vastly smaller in scale. Again, this could be a fluke, or it could be a sign of some unknown systematic error in the way we've analyzed the CMB. Or more interestingly, it could be a genuine hint of a preferred direction in the universe, a violation of isotropy. But the statistical significance is not overwhelming, and most cosmologists are inclined to wait for better data before drawing conclusions. There are also anomalies in the large-scale structure of the universe. Several structures have been discovered that seem to be larger than what should be possible given the age of the universe and the time available for structures to grow. The Sloan Great Wall, the huge LQG, a large quasar group, and the Hercules Corona Borealis Great Wall, which may stretch for 10 billion light years, though its existence is disputed. If these structures are real and as large as they seem, they might challenge our understanding of how structure forms in a homogeneous universe. And then there's the Hubble tension I mentioned earlier. Two different methods of measuring the current expansion rate, the Hubble constant, give different results. The CMB-based method gives about 67 kilometers per second per megaparsec. The supernova-based method gives about 73. That's a significant discrepancy, about 9%. And it doesn't seem to be going away as measurements improve. In fact, the discrepancy has grown more pronounced with better data. One possible explanation is that we're in a local underdensity, a region where the density is lower than the cosmic average. In an underdense region, the local expansion rate would be higher than the global average, which could explain why the local measurement gives a higher value. But this would be a significant violation of the cosmological principle, because it would mean we're in a special location at the center of a large, underdense region. Most cosmologists are not ready to throw out the cosmological principle based on these observations. The anomalies might have mundane explanations, statistical flukes, or systematic errors, or something we haven't thought of yet. But they're certainly intriguing, and they're being studied intensely. If any of them turn out to be genuine violations of the cosmological principle, it would force a radical rethinking of our understanding of the universe. For now, though, the cosmological principle stands. The universe appears to be homogeneous and isotropic on the largest scales, and that means it doesn't have a center. So here we are at the end of our journey. We started on Earth, traveled outward through progressively larger structures, the solar system, the Milky Way, the local group, the Virgo Supercluster, Laniakea, the Shapley concentration, the cosmic web, the observable universe. At every step, we looked for a center and found none. We learned that the Big Bang didn't happen at a point in space, but everywhere at once. We learned that the expansion of the universe is uniform, the same from every vantage point. And we learned about the cosmological principle, the idea that the universe is fundamentally the same everywhere on large scales. All of this leads to an inescapable conclusion. The universe doesn't have a center, not in any meaningful sense. Or, to put it more poetically, every point is the center. You sitting wherever you are right now are at the center of the observable universe, because the observable universe is defined as the sphere of space from which light has had time to reach you. An alien on a planet 40 billion light years away is at the center of their observable universe. A civilization in a galaxy in the Shapley concentration is at the center of their observable universe. This is not because we're all in special locations, It's because there are no special locations. The center is everywhere because there is no center. It's a paradox that makes perfect sense once you understand that the universe isn't a thing sitting in space, but is space itself. And that space doesn't have a center any more than the surface of a sphere has a center. There's something profoundly humbling about this realization, and also something strangely comforting. We're not at the center of the universe because nothing is at the center. We don't occupy a special place, but neither does anywhere else. In the grand scheme of cosmic structure, every location is equivalent. The same laws of physics apply everywhere. The same cosmic evolution has played out everywhere. An astronomer a billion light years away would look up at their sky and see the same kinds of structures, filaments and voids and clusters that we see when we look at ours. And yet, paradoxically, we are special. Not because of where we are, but because we exist at all. The universe is mostly empty space, vast distances filled with nothing. Stars are rare. Planets are rare. Life is even rarer, perhaps vanishingly so. And intelligent life, capable of asking questions about the nature of the universe. We might be the only example in our entire observable universe, though that seems hard to believe given the sheer number of planets that must exist. But whether we're common or rare, the fact that we're here, that matter has organized itself into complex structures capable of contemplating their own existence, that's the real miracle. We exist at a special time, too. Not a special location, but a special epoch in cosmic history. We live after the era of structure formation, so we can see galaxies and clusters and the cosmic web in all their glory. But we live before the era when dark energy will have pulled most of the universe beyond our horizon, when the sky will be dark and empty. Future civilizations, if any exist, will have a much more limited view of the cosmos. They might not even be able to discover that the universe is expanding, because they won't be able to see distant galaxies receding. They might think their local cluster of galaxies is the entire universe. We're lucky. We live at a moment when the universe is revealing its secrets to us, when we have the technology to observe the cosmic microwave background, to map the distribution of galaxies across billions of light years to measure the acceleration of cosmic expansion. We're living in the golden age of cosmology, a time when some of the deepest questions about existence are being answered. And one of those answers, one of the most profound and counterintuitive, is that there is no center to it all. The universe is a centerless, boundless expanse, possibly infinite, expanding from every point at once. We're not at the middle of it because there is no middle. We're everywhere and nowhere, just like every other point in space. This realization has philosophical implications that extend beyond physics. For thousands of years, humans have struggled with questions of meaning and purpose, often tied to ideas about our special place in the cosmos. Ancient cosmologies placed Earth at the center because it seemed natural that the stage of human existence should be the focal point of creation. The loss of that central position, first with Copernicus, then with the realization that the sun isn't special either, nor is the Milky Way, has been called the Copernican principle, and some have seen it as a kind of cosmic demotion. But there's another way to look at it. If the universe has no center, then no place is more or less significant than any other. Every location has equal claim to being important. And if that's true, then the importance of any place, including Earth, comes not from its cosmic position, but from what happens there. We're significant not because of where we are, but because of what we are and what we do. The universe is vast, unimaginably so. The numbers we've thrown around in this video, millions of light years, billions of galaxies, trillions of stars, become almost meaningless because they're so far beyond everyday experience. It's easy to feel small and insignificant in the face of such immensity. But remember, the universe may be vast, but most of it is empty. Most of it is the cold, dark vacuum between stars and galaxies. The interesting parts, the parts where matter has organized into complex structures, where stars shine and planets orbit, and on at least one planet, life has arisen and asked questions about it all. Those parts are rare. You, a conscious being capable of contemplating the cosmos, are one of the universe's ways of understanding itself. That's not a privileged position in space, but it is a privileged state of existence. So while we may not be at the center of the universe in a spatial sense, we are, in another sense, at the center of the universe's ability to reflect on its own nature. Because without minds to observe it, to measure it, to wonder about it, what would the universe even mean? This is the conclusion of our journey to the center of the universe. The center is here, where you are right now, and it's also everywhere else. It's a concept that exists only in the mind, a useful fiction we once believed, but now know to be just that, fiction. The real universe is stranger and more beautiful than a simple model with a center point. It's a four-dimensional space-time fabric, expanding and evolving according to the laws of physics, filled with structures on every scale from the subatomic to the cosmic web. And we're part of it, not at the center, but participants nonetheless. Our observations help map its structure. Our theories help explain its evolution. Our existence proves that the universe is capable of producing consciousness, of creating beings who can ask, "Where is the center?" and figure out that the question itself is based on a misunderstanding. So the next time you look up at the night sky and see the stars, remember this. You're seeing light that traveled for years or centuries or millennia to reach your eyes. You're seeing photons that began their journey in distant suns, traveled through the expanding space of the cosmos, and ended their journey by striking your retina. And from the perspective of those distant stars, you're at the center of their visible universe, just as they're part of yours. We're all centers, and none of us are centers. It's a beautiful paradox, and it's one of the most profound truths we've discovered about the nature of reality. If you found this journey through the cosmos mind bending and fascinating, make sure to hit that like button and subscribe to Behind the Space. We're constantly exploring the deepest questions about the universe, from black holes to dark matter, to the ultimate fate of everything. Drop a comment below telling me what aspect of this journey blew your mind the most. Was it the size of Laniakea? The idea that the Big Bang happened everywhere at once? The concept that every point is the center? I read every comment, and I love hearing what resonates with you. And if you want to dive even deeper into cosmic mysteries. Check out our other videos on the expansion of the universe, dark energy, and the structure of space-time. There's so much more to explore, and I can't wait to take you on more journeys through the cosmos. Until next time, keep looking up and keep wondering about your place in this magnificent, centerless universe.